Okay, so enthalpy symbolizes H, of course. Changes in enthalpy are delta H. We can't really measure enthalpy directly, only the changes. If heat is released, the heat content of the products is lower and delta H is negative, which means it's an exothermic reaction. If heat is absorbed, the heat content of the products is higher and delta H is positive, which would make it an endothermic reaction. So let's look at this potential energy diagram here. Is this an endothermic or an exothermic reaction? Well, the change is going down. This is a downhill reaction, which means the products have lower energy than the reactants. So that means delta H is going to be less than 0 or negative. Heat is given off in this reaction. Okay, how about this one? Well, the change is up. We're going uphill. The products are winding up with a higher energy content than the reactant started with. So if we're going uphill, delta H is always positive or greater than 0, which makes it an endothermic reaction, one in which heat is absorbed. So let's look at the overview here. In any reaction, chemical or physical, it's going to involve the absorption or release of energy. The energy is usually measured in the form of heat, typically kilojoules, and is called the enthalpy, or simply the heat of reaction. That is symbolized as delta H in our equations. And enthalpy is usually measured at 101.3 kilopascals, that is standard pressure, and 298 Kelvin, which is actually slightly above standard temperature. So we'll talk more about those numbers, those specific numbers, and why we use those later. Okay, so how do you solve for delta H? Well, if they give you a graph with numbers, your job is really easy. You can just do the math. Of course, you need to memorize this formula. Delta H is potential energy of the products minus the potential energy of the reactants. So here's an example question here. We have a potential energy diagram. So you see that this diagram has a big kind of bump in it, unlike the other ones that I had on the screen earlier. We'll talk about that bump later. It's really not important. But we have our reactants on the left, and we have the progress of the reaction going, and then we always have our products on the right. So this graph has numbers. The potential energy is measured in kilojoules on the y-axis here. So take a minute and solve for the delta H of this reaction. Okay, so we use our equation, potential energy of reactants minus potential energy of, that should say, potential energy of products minus potential energy of the reactants. So our products' potential energy is 20 kilojoules. So our products C and D are 20, and our reactants A and B are 40. It's always the ending, the products, minus the beginning, the reactants. So 20 minus 40, of course, is negative 20 kilojoules. The negative tells me it's an exothermic reaction, which makes a lot of sense because despite this big bump in the graph here, we're going downhill overall. The change in this graph is down. Okay, so what if they give you a graph but don't give you any numbers? Just pretend to do the math. So you know the equation is potential energy, again, that should say products minus potential energy of reactants. So in this graph here, if they want you to characterize the delta H, is this endo or exothermic, or would delta H be positive or negative? There's a couple different ways to do this. So if I use this equation, again, slight typo, potential energy of products minus reactants. Let's look at my products. Now, there's no numbers here. I could definitely put some in, but let's just look at where they are. C, my product, is a big number, okay, because it's higher than AB. It's bigger than AB. So if I have a big number minus the potential energy of the reactants, which are AB, it's a small number. Whenever you have a big number minus a small number, you're going to get a positive number. So positive delta H's, of course, are endothermic. The other way is to just kind of memorize that we're going uphill here. We're absorbing energy. Endothermic reactions absorb energy. Endothermic reactions have positive delta H's. But what if they ask you to solve for delta H when they just give you an equation? So like what if they said, what is the enthalpy of the reaction when 2 moles of hydrogen gas combine with 1 mole of oxygen gas to produce 2 moles of gaseous water? Well, the answer is use table I. So these are some of the most difficult reference table questions I see on the Regents because kids often don't know that this is a table I question. If you turn to table I, you will see heats of reaction. And they'll even tell you that it's at those temperatures and pressures that we talked about, standard pressure and that 298K. It's the only time these two numbers will come together. Okay, so pitfall number 1 when using table I, like I said, is realizing that you're answering a table I question. The giveaways is they're usually asking about delta H. This is the only table that asks you about delta H. Sometimes they'll say according to table I, sometimes they won't. If you get to a question, usually a multiple choice question, and you ask yourself, how am I supposed to know this? It's probably a table I question. I see this stumping kids all the time. Like I said, if the question is about delta H or uses words like exo or endothermic with specific equations, chances are it's a table I question. Also, if they discuss those specific units, like I said, those numbers will only appear next to each other. Standard pressure in that weird 298K, those numbers will only appear next to each other when it's a table I question. Pitfall number 2 when using table I is confusing positive and negative delta H's. So the good news is they actually give you a little cheat sheet. They clue you in down at the very bottom here. It says the delta H values are based on molar quantities represented in the equations. Okay, that's nice. And then at the bottom, a minus sign indicates an exothermic reaction. So if you see a little minus sign here, like these bottom two, that's an exothermic reaction. If you see a positive, that's not. It means it must be an endothermic reaction. Pitfall number 3, the phase or the state of matter for the reactants and products is important. Okay, so let's look at 2 examples here. So if they asked you this question here, and they're asking about gaseous hydrogen and gaseous oxygen making gaseous water, you'll get this delta H, negative 483.6. But if they're asking the same equation, but the production of liquid water, it has a completely different delta H. So you might just see these compounds and quickly look at maybe the first one, but if you fail to realize that the product is liquid water, you'll get the question wrong. It's a little tricky question sometimes. Pitfall number 4 is that the delta H values are based on molar quantities represented, like it says at the bottom of table I. So if the molar quantities change, so will your delta H. So let's look at an example here. Given the reaction, what is the approximate delta H for the production of 1 mole of liquid water? Okay, so you actually don't need to look at table I for this one because everything you need is up here. So given this reaction, I am producing 571.6 kilojoules of energy. But as you can see, that is for the production of 2 moles of liquid water. So what would be the approximate delta H for the formation of 1 mole of liquid water? And here are your 4 choices here. Go ahead and make your selection. Okay, so it's not going to be 3. Like I said, our delta H would be negative 571.6, but that's for the production of 2 moles of water. Okay, the answer is also not going to be 4 because this is an exothermic reaction. I know this because energy is a product. So it's not going to be positive. My delta H is definitely going to be negative, but it's going to be half of the actual delta H because I'm only making 1 mole of water. So that's choice 1. So in summary here, you should now be able to solve for enthalpy or delta H given a change in temperature. You just need to use the formula, Q equals mc delta T. You should also be able to solve for enthalpy if given a potential energy diagram. If you use the formula, the potential energy of the products minus the potential energy of the reactants. Remember, this is a formula you need to memorize. This first one you don't. This is on your reference table on table T. This one is not, but it's very, very handy if you know it. Exothermic reactions always have a negative delta H. I hope you memorize that, but if you don't, remember there's a little cheat sheet at the bottom of table I that will remind you this. And the opposite is true. Endothermic reactions have a positive delta H. You should also be able to use table I to answer questions about enthalpy. There's a lot of pitfalls with table I, like I showed you. We'll practice some of these in class. But after enough practice, table I usually is no problem for most kids. That's it for table I. If you have any questions, please let me know.